We're going to finish off this unit by looking closely at a program I think has been very well designed for security. It's called, appropriately enough, Very Secure FTPd. FTP stands for File Transfer Protocol. This is a protocol that was particularly popular prior to the rise of the World Wide Web, but you can still find FTP servers around today. It is used to allow clients to upload and download files to and from remote servers. In the 90s and early 2000s, there seemed to be a never-ending parade of compromises to FTP server software. VS FTPd was written in response to this poor state of affairs. It is a very thoughtful design aimed to prevent and mitigate defects. At the same time, it aims to get good performance. For example, it's written in the C programming language rather than a higher level and type-safe language like Java. It's written and maintained by Chris Evans, and as far as I know, there has never been a recorded security breach against it.
Let's start by considering the VS-FTPd threat model. First, we assume that clients are untrusted until they are authenticated. And once they are authenticated, they are granted a limited trust, that is, trust according to the user's file access control policy for those files being served by FTP, and of course all others should be inaccessible. The possible attack goals of an adversary are to steal or corrupt resources, for example, to download files that shouldn't be downloadable or to upload malware. Remote code injection to take over the server. The circumstances might be that a client attacks the server, or that a client attacks another client trying to snoop information or to corrupt it. Alright, now let's look at some of the defenses employed by VS-FTPd's design. The first defense is the use of a secure string library. Here on the screen we see the code for implementing all strings that are used by VS-FTPd. The first element is the normal zero-terminated C string. The next element is the actual length of the string. That is, it's what you would get if you'd called strlen and the first element is well defined. That is, it actually has a zero terminator. The third is the size of the buffer that was returned by malloc. Now, of course, the length of the string might be far less than the length of the overall buffer, and so we need to track both of those, particularly when we consider being able to concatenate strings together. To use VS-FTPd secure strings, we simply need to replace all occurrences of where we would normally use a char star, that is the normal C string, with a struct myStir, and we would replace things like stircopy with the equivalent function stir_copy. Here we can see the stir_copy function is implemented by a call to a private function, private stir alloc memchunk. The private function takes the pdest, this is the myStir of the destination of the copy, and from the source it takes the original C string buffer, pbuff, as well as the declared length that that buff should have. Now let's look at the code for private stir alloc memchunk. We can see that this code implements a number of defensive checks for the protection of security. The first check checks for integer overflow when we account for the added zero terminator that's going to be put on the end. If len plus 1 was less than len, then that implies that it wrapped around and overflowed. Next, we make sure that we have sufficient space in the target buffer per pstir to contain the source, and if not, we free the old buffer and allocate a new one. And then finally, we copy in the source contents up to the declared length, and we are sure to add the zero terminator at the end. The next defense that Very Secure FTPd employs that we'll consider is a secure system call library. And this addresses the common problem of error handling. Libraries often assume that arguments are well formed, and clients assume that library calls always succeed. For example, consider malloc. What if the argument to malloc is non-positive? We saw earlier that integer overflows can induce this behavior and lead to buffer overruns if malloc accepts, say, a 0 for its argument. Another question is, what if malloc returns null? Oftentimes, a dereference of null will cause a crash, which is safe, but on platforms without memory protection, a dereference can cause corruption and create security problems. VSFTPD's solution to this problem is to wrap system calls and make sure that the error checking happens in the wrapper so that clients can't forget to do it. Here we see that the size argument is checked. It should not be greater than the maximum integer, and it should not be 0. On the other hand, we also check that malloc does not return null, and if so, we kill the program immediately. As such, this routine is going to fail if it receives malformed arguments or runs out of memory. Another defense that VSFTPD uses liberally is to minimize privilege. For example, untrusted input is always handled by non-root processes, thereby minimizing the amount of privilege they have. When root-level actions are required, IPC is used by those processes to send a message to a root process to perform the few actions that require root access. During execution, processes reduce their privileges as much as possible, either running as a particular user, for example the one whose files are being served, or by using capabilities or the Linux seccomp system call to reduce the set of system calls that the process can actually use. VSFTPD also minimizes a process's access to files on the host system by hiding all directories other than the one that's serving files. All of these things are a kind of principle of least privilege, and minimizing the amount of root code tries to minimize the trusted computing base. So let's look visually at how VSFTPD operates. Here we have a server and a client. The client sends a TCP connection request to the server in an attempt to start an FTP session. Upon receiving this request, the server forks and execs to create a command processor. This command processor then forks again to create a login reader, and the login reader now runs at lower privilege. The client can then send the user and password to the login reader, and the login reader will then send the user and password request to the command processor, which will, using its root privileges, check whether or not this user and password is in the system's password database. If so, the user is authenticated and allowed to proceed. At this point, the command processor forks again and creates another reduced privilege command reader and executor that the client can then interact with. So the client could ask to change directories or to chown a file, that is, change the ownership of the file. Because chown is a privileged operation, this is delegated to the root command processor. Eventually, the client completes and logs out, and all of the processes associated with that client are cleaned up. Okay, so given this design, what attacks are possible? Well, the first attack we might consider is one at login. Suppose that during the login process, the client tries to inject a string to overrun a buffer or perform some other malicious action. Well, in this case, the login reader is whitelisting its input. It's only allowing user password and ignoring everything else. As a result, it limits the attack surface, making it hard for the client to penetrate the login reader. For that matter, the login reader has very limited privilege. It's not running as root. The authentication, in fact, is happening in the separate command processor process. As a result, this mutes the capabilities of any code that could be injected if there was a vulnerability in the login reader. Note that the client is not going to be able to communicate with the command processor directly. This is because of the way the connection is managed. And once again, the command processor, when it interacts with the login reader, accepts very limited input, so it's unlikely the client could fool the login reader into sending something malicious to the command processor. Okay, so let's imagine the client has logged in. What sort of attacks might the client attempt? Well, if they attempt the command reader, again, they're going to be limited in their capabilities. The command reader is not root. Though it does handle most of the commands, these commands are only at a lower level of privilege. Those that do require privilege go back and forth between the command processor and the command reader. If the client attempted to speak to the command processor directly, again, that's not going to be allowed, and those commands that are exchanged between the command processor and the command reader are very limited. The last attack that we might consider is one client trying to attack another via the FTP session. So let's imagine how that could happen. The first client connects and creates a command reader or executor, and then the second client does the same thing. Now these two clients have sessions between their respective processes. These sessions are isolated. They're in separate processes. As a result, there is no way that the command reader can talk to the client that it's not designated for. There are a few other things to say about VS-FTPd's design. Interestingly, it has a secure sockets option for encrypted connections, but it's not turned on by default. There's an interesting comment in the release notes for VS-FTPd that says it's a massive quantity of code which is essentially parsing complex protocols. As such, it's potentially not trustworthy. And as it turns out, the recent Heartbleed bug shows that that was in fact the case. Also, VS-FTPd attempts to reduce its attack surface by trusting as few third-party executables as possible. For example, it does not use the standard ls command for directory listings, but instead constructs its own directory listings in its own code.
The software development lifecycle consists of some organization of roughly 4 phases. In this unit, we have carefully considered how security fits into the first 2 of these phases, requirements and design. In earlier units, we spent a lot of time considering implementation issues and various security bugs and how to prevent them or mitigate their effects. Next, we're going to consider the last phase, testing and assurance. In particular, we're going to discuss how to use automated code review to find security bugs using techniques like static analysis. We're also going to look at a technology called symbolic execution that forms the core piece of a technology called automated white box fuzz testing. This technology is very good at finding certain sorts of bugs. Finally, we'll look at the general practice of penetration testing, which aims to find security problems in a completed system involving various tools employed by testers with their black hats on.